So this beautiful diagram is considering a particular figure. Okay, let's just say it's a block. Okay, please forget about the fancy mathematics. We only need an understanding of this. So we are looking at a particular body that is sitting on top of a slope. And as it is on the slope, so let's take, for example, this, and I have a body sitting on top of it like that. We are trying to use this diagram to show the various forces that are sitting on top of this body that is going to experience the failure. And so we have a force. Before any failure can occur on a slope, there should be some kind of an initiation, which we have established as the discontinuity. And so one, there is a crack that will start the whole game. And once there is that tension crack within the material, there will be some forces pushing the material that has separated itself to fall. And that causes within the tension crack. Massa, if you are separating yourself, just fall and leave us the remaining ones to be stable. So that force is there on this body. Then there is an upward force if there is the presence of water also pushing the body upward to cause the failure. Then there will be another force. So you, the engineer, will want to come in to supplement or support this broken body from failing. And so you will come in with your bolting at a certain angle to prevent the failure. Then on the surface, you have your resistive force that is preventing the failure from occurring. And there is that normal force that is here preventing the failure. So one is coming down and this is being opposed by the U. And then this resistive force is also being opposed by what? This W sine phi. And this is the kind of forces that surrounds a given body on a slope. And so if it is this given body can be your dump truck sitting on a ramp. It has that tendency of sliding down, and there is that force preventing it from sliding. There is load in this truck exerted vertically. Then there is an upward force reacting on this particular truck. And so this could be anything at all you could picture sitting on top of a slope, the forces it is exposed to. And so at some point, if any point in time, if any of these particular forces exceeds the other, then there can be a reaction, which may be a failure where your dump truck will just lose control and start somersaulting downwards. If it is on the rock itself, it fails, and then everybody will start running for their lives. And that is it here. So we have the normal stress, which is what we mentioned here in this figure. So the normal stress, if you want to compute the normal stress, which is the W cos phi over A, the shear stress. So the shear stress here is talking about, you remember this formula. If you want to measure the shear strength, what did we say it was? The shear strength, tau, was equal to C plus this tan theta. So now instead of the normal thing, we are replacing this normal stress with what? That. Because now we are dealing with slopes. And then the angle with which we are perceiving the forces are different. So we are substituting this particular thing with just this fancy topic, which is the normal stress, the sigma here, is what was here initially. Then at the end of the day, we have the same, the shear stress being expressed. Then we have the resistive force, the R that you see here. There was an R here. So that R is what is preventing the sliding. And how do I compute that? To compute that, I need the cohesive times the area plus this value. So anything that is opposing the force, the resistive force R, can that. So the A here is talking about the area, the surface area upon which the body is sitting. And then the W is talking about the weight of that material. And then the angle, which is the internal angle of friction we computed earlier. Then the next thing we want to look at is the uplift force, the pressure caused by water existing within the material, which is also facilitating the failure. And that is also here. So the effect of water pressure is also computed or expressed in this form. So let's see the final expression. So to have an equilibrium where there won't be any failure at all or any sliding, then the forces, the resistive forces and the pore water pressure and other things must be equal, directly or proportional to the other forces that are generated within the material to resist the failure. So that is what we have here. So when bolting is used, when we bring in the bolt to avoid the failure or to enhance the stability, then that bolting is also considered in the expression, which is the T. And so I want us to have a look at one thing which we term as the factor of safety, which we have to all the time. So in order to compare the stability of a slope under any condition other than the limiting equilibrium, which is a situation where you are just concerned about whether all the forces are equal, we can also look for an index that we can use to describe whether we are safe or we need to put in further effort, is what we term as the factor of safety. And so with the factor of safety, we are looking at all possible forces that are generated internally to avoid failure. Then all other external stresses that are exerted on the body. If the ones that are exerted on the body are more than the ones produced by the body to avoid failure, then there's going to be failure. So we have a factor of safety, F equals this. So now, if you are more than one, if we express this and we have excess more than one, other books will say 1.5, others will say 1.3, depending on the type of material. Then you can relax as a geotech officer and say, oh, you are quite okay. Because whatever value you are going to get at the end of the day will determine on the safety parameters of your company. And so if your target is always to get 1.5 as the standard, if you get less than 1.5, then you put in your safety measures. It could be the bolting you are going to do in the stope, or some grouting or wire meshing or whatever that you need to do. So that is it for this factor of safety. So God willing, tomorrow we shall have a look at the types of slope failure. So the types of failures in terms of slopes are the circular, the plane, the wedge, and the toppling failures. So tomorrow we shall just have a brush over of all of these, and then we can end that of the topic, stability of soil and rock slope, and if possible, jump into pillar, and then we can end our lesson of applied rock mechanics.